Good morning. My name is Shruthi from Department of Electronics and Communication Engineering, BGS Institute of Technology, Adichunchangiry University, Karnataka, India. I am here to present my topic on TALOS, optimization of the CNN for the detection of the tomato leaf diseases. Here is the quick outline of what I will be presenting today. The presentation will begin with abstract and brief introduction to the topic. Next, the objectives of the research are considered. Following that, methodology and implementations are explained. Then, results of the experiment. Finally, it will conclude with the summary of the findings and future directions. Abstract. Early detection of the plant diseases is essential to ensure healthy crop yield and minimize financial losses. Convolutional neural network or CNN has emerged as a powerful tool in the image classification application because of their excellent feature extraction abilities. However, the challenges associated with the CNN affect the performance of the model. For example, the diversity of the images in the dataset, or the selection of the robust model, or it may be tuning of the hyperparameters in the model. These three factors are considered as a crucial in order to get the effective performance. By considering all these limitations, the proposed method consider a customized convolutional neural network which is aimed to train with the limited amount of the images. Along with it is able to provide limited number of the trainable parameters. So in order to get the effective tuning of the hyperparameters, the study consider the TALOS, a hyperparameter, automated hyperparameter tuning technique. After the conduction of the experiment, the result shows the CNN model achieves an accuracy of 94.7% with the 33,647 trainable parameters. So we can conclude that the approach not only optimizes the performance of the model, but it also reduces the manual trial and error method with the help of TALOS. So it can be considered as a scalable solution in agricultural technology. Introduction. Agriculture is considered as a main occupation in our country. About 75% of the population depends on the agriculture directly or indirectly for their livelihood. But the various factors like unpredictable weather condition or poor soil condition, attack of deadly pathogens, driven many away from farming. We need a technology, an automated technology as a solution so that we can detect the diseases and provide the solutions to the agricultural problems. Among all these problems, the attack of the pathogens or the attack of the diseases to the plants is considered as a crucial one. Recently, convolutional neural network or a part of deep learning is considered as an effective tool because of their excellent feature extraction abilities from the images. It is known for their extraction of the features, even the small details about the features from the images. But the performance of the CNN depends on various factors. Let's consider one by one. The data set which is used to train the any CNN model or deep learning model. The images in the data set should be able to provide all relevant features which is required by the model, so that the model and the later on in the later stages it is able to detect the particular diseases. So the images in the data set should be well processed, balanced, and it has a equal number of the classes. The second one is the robust designing of the model. We have to design the model. We have so many predefined models for which is different for different applications. So we have to customize those models according to our application. We need to decide the number of the layers. We need to define the hyperparameters and the other pre-parameters so that it provides the best accuracy or best performance. And the last one, optimization or the tuning of the hyperparameter is considered as a crucial one, because the hyperparameters plays a very important role. If we select any one of the hyperparameters wrongly, it may leads to overfitting or underfitting. So tuning plays a crucial role in order to get the good performance. So with the help of those limitations and research stuff, we have formulated the three objectives. The first one is the study mainly proposes the disease identification system for the tomato plant leaf diseases, which are collected from the plant village dataset with the help of customized convolutional neural network, which aim to provide the reduced parameter. The second one is the training of the CNN model with the limited data set of the tomato leaf images. And the third one, in order to enhance the performance of the CNN model, the proposed method considers the TALOS, automated hyperparameter tuning technique, which reduces the need of manual intervention. In order to implement those objectives, the following steps are considered. The first one is the collection of the data set from the predefined data set and the pre-processing of the images in that data set. Second one, the defining of the CNN architecture according to our application. The integration or the definition of the TALOS. We need to define the required libraries or functions. Then we have to integrate the TALOS with the CNN model. After that, we can conduct the experiment. Then finally, the visualization, the output from the TALOS experiment, we can select the best optimal set of the parameters. So in order to implement these methods, we consider the flow diagram as shown in the figure 1. The process begins with the collection of the data set from the plant village data set. Here we mainly focusing on the tomato leaf images, which are from plant village, and 3 classes: healthy leaf, light white, and yellow leaf curl. Once the data collection is over, we have to consider the pre-processing of the images, augmentation, resizing, normalization. This depends on the application. Then we have to define and we have to set up the TALOS. What are the requirements? What are the libraries and require the functions? We have to set up the TALOS. After that, we need to define the model. That means we need to define the number of the layers, number of the what are the parameters and other required functionalities, and we have to define what are the required. This is the crucial one. This is the important. We need to define, or we need to mention what are the hyperparameters and what is the related search space for that hyperparameters. In this proposed method, we consider 5 hyperparameters and 2 search space for each hyperparameters. Once the definition the search space part is over, we need to conduct the experiment. After the conduction of the experiment, it provides the visualization of all possible combination. Among all possible combination, we need to select the best one. That means the combination which provides the best validation accuracy and the lowest validation loss is the best hyperparameter combination. This completes the evaluation of the model. This slide shows the detailed explanation about the data collection and the pre-processing step. The dataset for this study was obtained from the plant village dataset, following 3 specific categories of the tomato leaf: healthy tomato leaves, healthy leaf, late white, and yellow leaf curl. Each of these classes contain 900 images in the training set and 110 images in the testing set. The dataset images were pre-processed so that the suggested model could extract the necessary features which are required for training and classification of the model. Here, the images, all the images in the data set are resized to 256 pixels to maintain the consistent input size for the CNN model. The figure 2 shows the sample images which are collected from the training data set. The figure is about the customization of the CNN model, which is adapted in our proposed method. From the figure, we can see that there are two main stages: feature extraction stage and the classification stage. As the name indicates, feature extraction stage is solely dedicated to the extraction of all fine detailed features from the input images, input data set. After the extraction is over, the classification stage perform the classification and provide classify the images according to the classes. Then let's consider the feature extraction stage. Here, we can say that there are 3 convolutional layers: convolutional 1, convolutional 2, and convolutional 3. These layers are responsible for extraction of the features. For example, convolutional 1 extract the features from all input images which are present in the input data set. After that, the convolutional 2 again extract the fine features, detailed features which are comparatively better than convolutional 1. Again, convolutional 3 compared to 1 and 2 get the fine detailed features. So if you want to get a fine details of the features, we can add 1 more layers. After that, It provides the set of all it provides a set of all features which are present in the input images. Once the feature extraction stage is over, the extracted features are flattened and passed through the fully connected layers. In the fully connected layers, the dense one layers reduces the features image into 1D vector. The dense layer 2 reduces the output to a small vector size. The softmax layers provides the final output probability for each class. At last, the final output is the classification of the input image into one of three classes corresponding to the different type of the input images defined at the beginning stage. This is the key parameters we need to define at the initial stage of the CNN. Filter size, here we consider 3x3 filter size. A number of the filters 32. Pooling is the max pooling with a 2x2 pooling window and 1x1 stride value. Activation function is ReLU, rectified linear unit or exponential linear unit, and the categorical cross entropy is used as a loss function. This figure mainly shows the how the TALOS tool works. The start, here the process begins. Then we have to prepare and test the model. Once the model is prepared, we have to test the model. We have to test a model for the given input images. If the model is working properly, we can move forward. If the model is not working, we have to modify the model till it works. Again, we need to check that model until it works satisfactorily. Once this part is over, next we can go for hyperparameters. In the hyperparameters, we need to select what are the hyperparameters and what are the search space for each hyperparameter with the help of TALOS parameter dictionary. Once the hyperparameter space is defined, we can conduct the experiment and explore the different parameter combination. And that from that combination, we can take the best configuration. We can run the experiment and evaluate the result. Then we can evaluate, while evaluating the result, we can test for which combination the TALOS is providing a highest validation accuracy and a lowest validation loss. If it is satisfactory, if the result is satisfactory, we can complete the experiment and get that combination as the best combination of the hyperparameters. This is the result part. In the result part, there are two main graphs are plotted. First one is the confusion matrix, and the second one is the validation accuracy and the last curve of the CNN model. Let's consider the confusion matrix. Here we mainly consider the three classes, hence the confusion matrix is the 3x3, class 0, class 1, class 2. Along x-axis the labels are predicted and y-axis the true labels are plotted. Let's consider the class 0. In the class 0, the model predict or model classify all 110 images correctly. In the class 1, the 93 images are classified correctly, but 6 images are classified as class 0 and 11 images are classified as class 2. Whereas in class 2, all 110 images are classified as class 2. So this shows the model is learning well and providing good accuracy. The few misclassification is because of the features of this class. Few of the features from this class are overlapping with the features of the other classes. So because of that, we may get the few misclassification. Then consider the validation accuracy and the validation curve of the CNN. Here we can see that the model is trained for 10 epochs. At the initial stage, the accuracy is low, that is below the 0.5, that is below the 50%. Once the epochs at the training goes on increases, at the sixth, between 4 to 6, it steadily increases to nearly 90%. So at the ninth epoch, it exceeds the 90%. So we can keep on training the model till it reaches the steady value. So at 10th epoch, we get the accuracy nearly 95%. Whereas in validation loss curve, it's opposite to the accuracy curve. Initially, it is high. The loss is very high. We can see that at the 0th epoch, the loss is at 1. So as the epochs are the training continues, the loss is steadily decreases towards the 0.2 or below the 0.1. So by the 9th epoch, the loss drops to around 0.2. So it reflects the better predictive performance. The downward trend in loss suggests that the model is not overfitting and generalized well to unseen data. This is the visualization of the TALOS experiment. As I already mentioned, we consider 5 hyperparameters and 2 search space for each hyperparameter. So totally 2 to the power of 5, that is 32 combination. The TALOS provide 32 different combination, and for each combination it provides the accuracy, LAS, validation accuracy, and validation LAS. So in order to get the best one, we need to check for which combination the TALOS is providing highest validation accuracy and lowest validation LAS. In the figure, we can see that at the 25th round, it provides 94.7, which is the highest one. For that, we are getting 0.14 as the LAS. So we can consider the combination which are present in that round as the optimal performance or optimal set of hyperparameters. So we got the output as among ReLU and ReLU and Adam is 3D Adam 0.25, 0.5 is 0.25 dropout, and 0.25 is the convolutional dropout, and 128 as the dense neuron. So in other methods, in any other random search or grid search, we have to check each and everything manually. This is like a trial and error method. Whereas in TALOS, it automatically checks and provide all the combinations. It automatically checks and visualize. We can visualize the result also. So it reduces the searching time. It also reduces the searching time. So after the conduction of the experiment, we can conclude that the study mainly focusing on the detection of the plant, detection of the diseases in tomato leaves, which we here in the present method, we mainly consider 3 diseases. The customized model is trained only with the 3030 tomato leaf images. Even though we consider limited data set, it is able to provide a good accuracy. For the experiment, for the tuning of the hyperparameter, the experiment conducts consider the TALOS. Even though TALOS being is computationally is high, it narrows or it reduces the searching space of the hyperparameters. So tuning, making this tuning is more effective, and it is also suitable for the large models. So we can finally conclude that the model, what we proposed, is able to work with limited data set, and it is able to provide limited number of the trainable parameters, that is 33,647, and it is able to provide good accuracy of 94.7% with the help of automatic tuning technique, that is TALOS. So the impact of the hyperparameters is greatly affect the performance of any neural network model. So while conducting or while training any neural network model, we need to consider 3 main factors: the images in the data set, the robust model selection of the designing of the robust model, and the tuning technique which is used for hyperparameters. So in the future, we plan to extend our work to the other deep learning models also, and we plan to consider the other types of the classes with more number of the classes. With more number of the diseases. So the proposed method is mainly useful for the farmers to detect the diseases in the plants as early as possible. We can implement this method as a mobile app also. This is the few references I have got through while conducting an experiment. So thank you for giving me opportunity to present my topic. Thank you.